All right, let's take a look at this problem. We've got a Boeing 777-200 LR loaded at 92% of its maximum takeoff weight. It takes off from Dubai International Airport. It's 24.4 meters elevation during an average day in July. It's 34.5 degrees Celsius with a standard pressure for the day of 101.3 kilopascals. 777-200 has a maximum takeoff mass of 347,452 kilograms, and its wing area is 427.8 meters squared. We're going to assume the takeoff speed is 376 kilometers per hour, and we want to know what the minimum coefficient of lift needed at the point where the aircraft just lifts off the ground. All right, let me get a clean sheet of paper here. All right, so let's write down the information that we know. All right, we're at 92% of the maximum takeoff weight of 347,452 kilograms. We're at 24.4 meters elevation. It's 34.5 degrees Celsius. The pressure is 101.3 kilopascals, and that should actually be a capital P. The wing area is 427.8 meters squared, and its takeoff speed is 376 kilometers per hour. All right, so the first thing we're going to do is convert mass to weight. Okay, our weight equals the mass times gravity. Now here we're at 92%, so we're going to say our weight is 0.92. We change a percent to a decimal by dividing by 100, so we get 0.92 times 347,452 kilograms times 9.81 meters per second squared. All right, so take a minute, work that out, and see what you come up with. All right, so when we work that out, we come out with 3,135,825 newtons. All right, now we want to convert kilometers per hour to miles per second. All right, so we're at 376 kilometers per hour. Take a minute and see if you can convert that to miles per second. Okay, making this conversion. We can take our 376 kilometers per hour, and usually we'd have that 376 as a coefficient out here, But for the canceling, I just think it's easier if I go ahead and just put it in the numerator where it would go. And we're going to multiply that times, there's 1 hour is the same as 60 minutes. So our hours have canceled out. So now that we're at kilometers per minute, times 1 minute is the same as 60 seconds. Okay, now we've got kilometers, and I want that to meters per second. And so a kilometer is 1,000. So when I get my calculator, let's see what we come up with here. Okay. That's going to be 1,000 meters is kilometers, so our kilometers cancel out, and I come out with 104.4 repeating. Okay, so that comes out to be 104.4 meters per second. Whoops. All right, now let's calculate the air density. So we've got rho equals our pressure divided by 0.02869, and that's just part of the equation. Kilojoules times K times our temperature plus 273.1 degrees Celsius over Kelvin over degrees Celsius. All right. Take a minute and see if you can calculate the air density. All right, so we're going to fill in our values here. And again, I'm not going to make you put the units of measure, because I know that when I do my calculations, if I put everything in correctly, I'm going to come out with kilograms over meters cubed. So I'm just going to do 101.3 over my 0.2869 times our 34.5 degrees Celsius plus 273.1 degrees Celsius. Using my calculator, divide this out. Let's see, so I come out to approximately 1.148 1.8 kilograms per meter cubed. And if you round that off to 1.15, that's fine. 1.2 might be rounded off a little bit too much. Either way. Okay. Now we want to calculate the coefficient of lift. And on your reference page, the coefficient of lift is 2 times lift, area of the wing, times rho, which is your air pressure, times the area squared. Okay. All right, so take a minute and see if you can calculate the coefficient of lift. All right, so working this out, we've got 2 times, or 3,135,825 newtons. Over 427.8 meters squared times 1.148 kilograms per meters cubed times 104.4 meters per second. All right, so our coefficient of lift at takeoff under the conditions they gave us is 3. Nope, I left my squared off there. And I come out with 1.171650678. We'll just round that off to 1.17. And there are no units for the coefficient of lift, so our final answer will be 1.17. All right. If the same aircraft has a coefficient of lift of 1.24, how much extra lift is available for climbing off the runway? All right, so on this one, we're going to take a look at, let's see. All right, so our lift formula, the coefficient of lift times the area of the wing times our rho times our velocity squared divided by 2. All right, take a minute, fill in the values, and see what you come up with on this one. All right, filling in our values, we've got 1.24 times our 427.8 and that's meters squared, times 1.148 kilograms per meters cubed, times our 104.4 meters per second squared, divided by 2. So we just multiply straight across, divide by 2, and our lift comes out to 3,318,756 newtons. All right, so now take a minute and see if you can calculate the extra lift available. Okay, so all we have to do on this one is take our 3,318,756 minus what we calculated earlier is our lift, which was 3,135,825 newtons. So that comes out to 182,931 newtons. Rounded off, we come out with 183,000 newtons. Okay, the sailing aircraft lands in Hong Kong after a long flight, over 5,950 kilometers, that used 82,900 liters, which is 21,900 gallons of fuel. Assume the same 1.24 coefficient of lift, and that the jet fuel burn weighed 0.803 kilograms per liter, or 6.7 pounds per gallon. Hong Kong average summer temperature is 91 degrees Fahrenheit, or 32.8 degrees Celsius, with a standard pressure for the day of 101.29 kilopascals. What is the minimum speed at which the aircraft can land? Okay. So the first thing we want to do is calculate the air density at the airport elevation. And before I do that, I'm going to go ahead and put down some of these values they've given us. It used 82,900 liters. We still have the 1.24 for our coefficient of lift. The fuel weighs 0.803 kilograms per liter. It's 32.8 degrees Celsius, and we're still at 101.29 kilopascals. All right. So take a minute and calculate the air density at the airport. Filling in the numbers, we've got 101.29 divided by our 0.2869. And I'm not filling in the units of measure here. Again, if you want to be precise, we can fill in the units of measure and we can do the cross-canceling. But I know that my answer is going to come out to kilograms per meters cubed. So we're just going to simplify this a little bit. In my math classes, I make them do the cross-canceling, but for our purposes here, I'm not going to require that. 273.1. Okay, so our pressure, or our air density comes out to 1.154 kilograms per meters cubed, rounded off. All right, now we want to calculate the fuel burned. And all we have to do on that one is multiply the amount of fuel times the weight. And up here I use the liters. If you want to use the gallons, I give you those values also. I just use liters on this one. Okay. So the fuel used was 82,900 liters times the 0.803 kilograms per liter, which comes out to 66,569 kilograms. All right, now we want to convert mass to weight. Remember, our weight equals mass times gravity. So take a minute, convert the mass to weight. Okay, so our weight equals, our mass was 253,087 kilograms times 9.81 meters per second squared, which equals 2,482,782 newtons. All right. So now we want to calculate the velocity. Now, if we take the formula for the coefficient of lift, which is 2 times the lift, area of the wing, times our density, times our velocity squared. All right, so now we're going to rearrange this equation. I'm going to multiply both times v squared and divide both sides by the coefficient of lift. So I've got, well, let me start the next line right here. So basically we just, since we're dividing both sides by the coefficient of lift, the coefficient of lift ends up in the denominator. We're multiplying both sides by velocity squared. Since it's in the denominator, it's going to come up there. So we've got velocity squared okay. Now to get the v by itself, to isolate the velocity, We take the square root of both sides. So V equals the square root of 2L area rho CL. All right. So take a minute and see if you can calculate the velocity. All right, filling in our values here. And we've got the square root, 2 times our lift, 2,482,782 newtons, divided by 1.246 times our 427.8 meters squared times our 1.154 kilograms per meters cubed. And then we work that out. We get approximately 90.1 meters per second. All right, so now we just need to convert the meters per second to kilometers per hour. Okay, so take a minute and see if you can do that. All right, so on this conversion, I'm going to take my 90.1 meters per second. I know there's 60 seconds in 1 minute, so there my seconds cancel out. Then there's 60 minutes in 1 hour. So my hours cancel out. So now I've got meters per hour. So we want kilometers. So 1 kilometer equals, 1,000 meters. So our meters cancel out. And we're left with kilometers per hour. So we multiply 90 times 60 times 60, divide that by 1,000, and come out with approximately 324 kilometers per hour. All right, now it says to use the landing speed calculated in the previous question and assume that the coefficient of drag is 0.087. How much drag will that same aircraft produce upon landing in Hong Kong? Okay, so I'm going to slide down here a little bit further. And I think I've got enough room on this page. All right, so we're going to calculate the coefficient of drag, which is 2d over aero velocity squared. All right, so now this time we need to get the d by itself. We need to get the drag by itself. So what I'm going to do is multiply both sides times the a rho v squared times the CD and divide by 2. And again, this just goes back to algebra. So that's going to equal Then I just divide both sides by 2. So D equals aero velocity squared, coefficient of drag, divided by 2. All right? So fill in numbers and see what you come out with on that. All right. So our drag is going to be what they gave us. Our coefficient was 0.087 times 427.8 times 1.154 times 90.1 divided by 2. So I come out with 174,335, which rounds off to about 174,000 newtons rounded off.